Okay, let's take a look at improper integrals. And improper integrals really are just looking at integrals that either have the possibility of having infinite area or maybe they have an infinite width, meaning their bounds involve infinity. So I guess we need to decide that an integral looks at the area under the curve, and we've always looked at situations where that area is a finite number. So we need to look at other situations. So let's look at this integral. This one's probably the most important one to start with. Let's integrate from 1 to infinity of 1 over x dx. And again, eventually you're going to get a feel for this guy, but right now, just go ahead and do the integral. And really, that's really always the case. Just do the integral, plug in the limits, and then decide based on that answer what happens. So the integral from 1 to infinity of 1 over x. Well, the integral of 1 over x is the natural log of x. And then we evaluate from 1 to infinity. So this is the natural log of infinity minus the natural log of 1. The natural log of 1 is just 0, and the natural log of infinity is infinity. So this is saying that this area under this curve, so if we graph this, starting at 1, well, when x is 1, 1 over x is 1, so we're at 1 comma 1, and then as what happens with 1 over x, well, it kind of decays closer and closer to 0, right? It asymptotically approaches that value. And what we're saying is that this area under the curve, when we break this up into an infinite number of rectangles, it's an infinite area, right? Not finite. And again, that's just something maybe new to us, but this red area is infinitely big, and we're going to use a word to describe that, and we're going to say that it diverges. Diverges, meaning it has an infinite area in this particular case. Okay, let's look at a different curve, and it's similar. 1 to infinity of 1 over x squared dx. Well, the integral of 1 over x squared is negative 1 over x evaluated from 1 to infinity. So that's negative 1 over infinity minus negative 1 over 1. Well, 1 over infinity is just 0, and negative 0 is just 0, so that's just 0. Then minus minus 1 is just 1. You're like, oh, okay. So the graph is similar, but it is not the same. Right? When you plug in 1 over here, you do get 1, but this thing goes, and it goes to 0 really, really quick, right? Because it's 1 over x squared rather than 1 over x. And it turns out that this area not only is a finite area, but the area is exactly 1. It's a finite number, and so we say that this integral converges, right? It has an area equal to 1 in this case, but really converges just talks that it could be a finite. I mean, it could have been 1, it could have been 4, it could have been 10, it could have been 100. Anything that has a finite area under the curve, we say converges, and anything that has an infinite area diverges. Okay, so we start thinking about the question. Okay, what could this power be? See how this power is 1 and this power is 2? Well, we start talking about the P series. And what is required of the power in order for x to some p to converge? When does this converge? And so you got to think that through a little bit. And what we can say is if p is strictly greater than 1, it converges. And if p is less than or equal to 1, the integral is going to diverge. And hopefully you can see that if the power is greater than 1, as in this example, when you integrate, the x stays in the denominator, and then when you plug in infinity, it doesn't cause an issue because plugging in infinity in the denominator just makes it 0. If it's 1 or less than 1 and you plug in infinity, the integral is going to be, the x is going to be in the numerator and cause a problem. Again, I'm going to show you an example of a p series. So what if it was 1 to infinity over 1 over the square root of x? The square root of x looks very similar, but it actually looks more similar to this guy. And And again, in this case, the p is a half. Half is less than or equal to 1, so we're going to claim that the p-series says that this diverges, and I can just show you that it diverges. If you increase the power by 1 and divide by the new power, you get that, right? Dividing by a half gives you a 2. Increasing the power from negative a half to a half gives you this, and then evaluate from from 1 to infinity. But when you plug in here, you get 2 square root of infinity minus 2 square root of 1. Well, that's just 2, and 2 times the square root of infinity. Well, the square root of infinity is infinity. 2 times infinity is infinity. Infinity minus 2 is infinity, which says you get an infinite area under this curve, which says it diverges just like the p-series suggested. Again, if this power is less or equal to 1, when you integrate, it's going to end up in the numerator, and plugging in infinity causes a problem. Again, if it's something like greater than 1, and the way, just give an example of 2, what if it was 1 over x cubed? Well, then again, when you integrate, you're going to get increase the power and divide, so you're going to get negative 1 over 2x squared. And that's me dividing by the new power to get a negative 2, increasing the power from negative 3 to negative 2, but then evaluate from 1 to infinity. Again, you're going to get negative 1 over 2 times infinity squared minus negative 1 over 2 times 1. Okay? This is just negative, this is 0, right? 1 over 2 times infinity squared, and this is minus minus a half, and so this ends up being a half. So this has a finite area, which is what the word converges means for an integral. It converges to a half. Again, this converges based on the p-series, this diverges based on the p-series, and even if you forgot that, you could actually just do the integrals and show that. And again, why are we having issues? Why do some converge and some diverge? Well, remember, we're making this x value, this width here, it's an infinite width. And that occasionally causes a problem. This infinite width causes an infinite area. This infinite width doesn't. Even though this is an infinitely wide kind of segment here, this goes to 0 so fast that it still has a finite area. And this actually doesn't go to 0 fast enough. It still causes an infinite area. So some of these improper integrals, again, improper integrals involving this, some of them diverge and some of them converge. The p-series is the most popular thing to kind of talk about. Okay, let's look at some other ones that are interesting. They frequently love you to look at inverse tangent. It's kind of a fun one. So what if I wanted to integrate, actually in this case, let's go from 0 to infinity of 1 over 1 plus x squared dx. If you think of the graph here, this graph kind of looks like this. It's actually kind of a hump here, but we're only looking at that one segment. And so we're looking at this area here. Is this area infinitely big, or is it some finite number? Well, this doesn't really work with the p-series. It's not exactly 1 over x to some power. It's 1 over 1 plus x to some power. So just go ahead and do the integral. This integral is actually just inverse tangent. So inverse tangent of x evaluated from 0 to infinity. And so you're like, all right, that's inverse tangent of infinity minus inverse tangent of 0. Well, inverse tangent of 0 is 0 because tangent of 0 is 0. So inverse tangent of 0 is 0. So that goes away. And then the question is, what's inverse tangent of infinity? And you got to remember, inverses are just going backwards. So this is the graph of tangent. Okay? This is at pi over 2, tangent is infinity. So if tangent of pi over 2 is infinitely big, then inverse tangent of infinity is pi over 2. So this value is actually just pi over 2, and so your answer here is pi over 2. And so what I'm telling you then is that this integral converges because it has a finite area. This area here is exactly pi over 2, which is a finite number. Okay, so that's kind of another example of a different function that you can look at to decide whether it converges or diverges. Okay? The other way you can look at an improper integral is you can look at a vertical asymptote. So we could look at, let's say, what if we wanted to integrate from 0 to 1 of 1 over x dx? And so now, instead of looking at the horizontal asymptote part, we're looking at this part. Integrating, again, as we let x get closer and closer to 0, we get this. And so what do you think about that area? So instead of an infinite width, we kind of have an infinite height here. Well, you're going to kind of develop some of those same things, but just do the integral. What's the integral of 1 over x? You get the natural log of x from 0 to 1. So you get the natural log of 1 minus the natural log of 0. The natural log of 1 is 0. The natural log of 0 is negative infinity. Negative infinity is infinity. And so in this case, this integral from 0 to 1 also diverges. It diverges. Okay, and we can go through that kind of scenario. What if this was 1 over x squared from 0 to 1? Well, we'd still have some issues. And again, you're going to have to learn the differences between integrating from 0 to 1 and integrating from 1 to infinity. They're kind of backwards of each other. Hopefully you can kind of reason why. So what if we looked at, basically it's the same graph, right? And in this case we get negative 1 over x from 0 to 1. And again, when you plug in 1, you get negative 1 over 1 minus negative 1 over 0. 1 over 0 is infinity, negative, and you get infinity again. So this also diverges. And it will turn out that actually if we make it smaller than 1, it'll be fine. Meaning 0 to 1 over 1 over the square root of x. Well, integrating this, increase the power, divide by the new power, you get this. And see how x is in the numerator now? So now when we plug in 0, we just get the square root of 0, which goes away, and the whole thing is just 2. Okay, so you have to kind of think about these two, 0 to 1 diverge, and this one actually converges, and you can compare that to what we talked about, the p-series of integrating from 1 to infinity. They're actually different. This doesn't get to infinity fast enough. You can start talking about those things, but really when you start talking about improper integrals, you're talking about integrals that either have infinite widths, because one of the bounds is infinity, maybe both of them are infinity, or you have some vertical asymptote that you have to deal with. And again, it's really not that bad. Just do the integral, evaluate the integral based on its limits, and then decide. In this case, we got an infinite area, and so we said diverges. This integral had an infinite area, so we say it diverges. This integral, we did it. We got some finite number, we say, okay, it converges. It has a finite area, meaning if you graph this one, and again, the graph looks almost identical to that, it actually has a finite area, meaning 2 square meters, 2 square feet is this, where in this particular case, it's got an infinite number of area. And that's really all improper integrals are. Occasionally, you are going to see, if you look maybe on a textbook or some college website, you might see something like this. They might say something, if you saw this, they might do something silly and say, this is really the limit of b as, we're going to look at the limit of this integral as b goes to infinity, and integrate from 1 to b of 1 over x dx. And I've always thought this was kind of silly. You're going to do this integral, you're going to get the natural log of x, evaluate from 1 to b, you're going to plug in b, natural log of b minus the natural log of 1, and then you're going to go back and you're like, all right, let's look at the limit as b goes to infinity, and then you're going to plug in infinity for b. That just kind of is just silly to me. I mean, I know it's maybe technically the right way, but aren't you really just doing the integral and plugging in infinity? Plugging in infinity and looking at the limit. I know infinity we can't actually plug in. Of course we can't. And we already know that because we already know limits. So if you see this, it's just doing the technical version instead of our way. You know, if you looked at my notes, or
or an examples on the keys, you're just going to see this. I'm going to do this. And I'm going to say that this is 0, and I'm going to say this is infinity, and then I'm going to be done. Where really, I'm letting it get really, really, really close to infinity, and I know then that limit, as I get closer and closer to infinity, the natural log of that is still infinity. But this you might see in a textbook, and I wouldn't worry about it much. The AP doesn't require you to do anything like this, because this is the problem they give you, and then this is the appropriate answer.